All right, let's take a look at the interrupt system on the 386 real quick. So on the 386, we have a simplified diagram here of how the interrupt controller, that's called the 8259 programmable interrupt controller, that's a part number, an Intel part number, how that connects to the 386 CPU. So there's a couple of important lines. Basically, you have a data bus. That's like a multi-wire bus that carries data. Usually that's used to connect the 386 to the memory system so that the 386 can read and write data to the memory chips on the board. But the programmable interrupt controller uses it too. And then we also have the interrupt line. That's one wire that goes from the interrupt controller to the 386 to alert the 386 that there's an interrupt that needs to be handled. And then the last one is the interrupt acknowledge line, INTA, that goes from the 386 back to the interrupt controller that allows the 386 to tell the interrupt controller that it's done handling the interrupt. So the way this thing works is basically the PIC has 7 interrupt input lines, right? Each of those is connected to a peripheral on the board. You know, think like the keyboard controller, the mouse, the serial port, all that stuff. Anything that could possibly need to interrupt the 386 gets an input line to the PIC. Okay, and then so as basically you can imagine, like the keyboard maybe, let's say, will throw an interrupt, and let's say the keyboard is connected to line I1, let's just say, and then as soon as the keyboard throws an interrupt, that's basically going to make line 1 go from a low to a high, and that's going to cause the 8259 PIC to then raise the interrupt pin that goes over to the 386. All right, and the 386 is going to then request the interrupt number from the PIC, right? It wants to know, okay, you said there's some interrupt, but I want to know now which of the 8 interrupt sources is the one that caused this interrupt. So the PIC is going to then put the number from 0 to 7 on the data bus, and that's the way that the 386 will know which of the 7 possible interrupt sources had caused the interrupt. Okay, so now by this time the 386 knows which of those interrupt sources is responsible for the interrupt, and now it needs to go and handle it somehow, right? So the way it's going to handle it is it's going to use its interrupt descriptor table. All right, and the interrupt descriptor table, usually on most processors, this is called an interrupt vector table. Intel is special, right? And so they have to call it the descriptor table. But it's really the same thing, right? This is just basically the huge array of function pointers. And each function pointer is basically just the address of a function that handles one of the interrupts, one of the possible interrupt sources, right? There's 256 of these things, right? Each one of them is called a gate, and it just holds the address of the handler for that interrupt, right? And so there's kind of 2 classes of interrupts that the CPU supports, right? All processors basically have the same setup, right? You have CPU exceptions, which are typically caused by some bad thing happening on the CPU, like some address error or something like that, an attempt to access an address that's not inside the process's memory space. That'd be caused by software. And that would be classified as an exception, right? Or, you might have some kind of a divide by 0 error. There's a lot of different things, a lot of different software problems that could cause a CPU exception. So the first 32 of these interrupt gates are reserved for the CPU exceptions, and they're defined by the data sheet for the 386. And then all the rest of them, right, there's a total of 256, so whatever 256 minus 32, all the rest of the interrupt gates are for hardware, right? And those are the ones that are controlled by this PIC, right? And so the hardware designer can basically hook any interrupt source up to any one of those hardware interrupts, interrupt gate 32, 33, 34, all the way up to 256. Okay, so the operating system's job is basically to populate this table with the addresses of functions that can handle these interrupts. So we're going to do that, and then once so we'll do that in software in a few minutes here. And then then the last thing we're going to do, so we're going to populate this table with a bunch of different interrupt handlers, and then the last thing we're going to do is we have to tell the CPU where in memory this table lives. Right? You can put this table anywhere you want in memory. It doesn't have to live at a hard-coded address. But when you create the table, then you need to populate the interrupt descriptor table register. This is a special purpose register inside the 386 that holds the base address of this interrupt descriptor table. Okay, so let's go over to our project, our operating systems project, and let's get started implementing this thing. All right, so here we are in the in a blank operating system repository that I just checked out. It's just like the stock thing. No changes have been made. So I'm going to open up the kernel main.c. You can see it's totally blank. So I think what we want to do here is set up some interrupts, and let's try and get the keyboard to interrupt the processor. And so in order to do that, we need to set up the interrupt table, and we need to set up the PIC, right? There's a little bit of configuration that needs to be done to the PIC. So let's just go ahead and start with the interrupt, the descriptor table, right? So the descriptor table has this kind of weird, kind of like descriptor format, where basically each entry in the descriptor table is not just a raw address. It has some extra metadata that comes along with it. So let's just make a struct that contains all of the data that we need to put in each one of those interrupt descriptor table gates. Okay, so this is a fairly complicated format here, but let me just go through and try and explain some of this stuff. So the offset field is kind of the most important field in this descriptor gate, and basically that's just the address of the handler function. For some weird reason, though, Intel, when they designed this descriptor table, they split that address up into two separate fields. So it's a 32-bit address, but it's split across two separate fields in this descriptor gate, right? So the least significant 16 bits, this is the least significant 16 bits of the address. And this goes in the the first 2 bytes of this gate, and then the most significant 16 bits of the address goes in the last 2 bytes of the gate. I have no idea why they chose to split the offset field up into 2 subfields like this. It just makes life so much more difficult, but that's what Intel decided to do. Okay, and then the next field after the offset, this is this code segment selector. Basically, Intel, the 386 has these different segments of memory that you can live in, right? And typically, when your operating system is running, there's 4 active segments, right? You have your kernel code and your kernel data, and then you have your user code and your user data. The total of 4 segments. And those segments are, set up by the operating system. They're initialized when the computer boots, and then they're pretty much not, changed again after boot time. Really, their only job is to enforce some privileges of memories. Just make sure that the user isn't allowed to access the kernel memory space. So the code segment selector, well, the one we're going to use is actually configured by grub when grub boots, right? Setting up the descriptor table for those things is a thankless job, and it's not worth our time. So we're just going to use the one that grub sets up. And grub configures this descriptor table to have the kernel code segment has an offset of hex 10 or decimal 16. So for each of these IDT gates, they're all going to be kernel code, right? They're code that's owned by the kernel, and so we're just going to configure every code segment selector field to be to have segment number hex 10 or 16. Okay, and then the 0 field, that is self-explanatory. That's just hard-coded to 0. And then the attributes field kind of just tells the processor what type of gate this is. Since this is a kernel mode 32-bit interrupt handler, we're just going to we're going to set this attributes field to 8E. All right, so you can go and read up on this if you want to. There's some documentation. You can either look at the datasheet for the 386 part, or you can read up on it on OS Dev Wiki. But anyway, it's not worth going into all the details of what that attribute field is. The key things that we want to do whenever we set these gates up is we just need to make sure we set the offset field to the appropriate offset within the vector table. Okay, so now that we have a struct defined for this, let's just we're going to create a vector table. And that's just going to be an array of these IDT gate things, and this is going to be 256 units long, right? So this is an array of IDT gates, and this is our our interrupt descriptor table here. Okay. And then last thing we need to do in order to initialize this descriptor table is we need to write a function that is going to be able to write to the individual elements in the descriptor table. We'll call our function setIDTGate. It's going to take 2 parameters. The first parameter it's going to take is the handler address. This is the function pointer to the function that handles the interrupt. And then the next parameter is going to be the gate number. Right? This is like the index into the descriptor table. Right? 0, 1, 2, all the way up to 255. Okay, so when we call this function, we're going to call this function for every gate in the descriptor table, and we're going to have this function basically take our handler address, split it up into low 16 bits and a high 16 bits, and set the offset appropriately, and then program that into the correct IDT gate. Okay. Oops, hang on. I think I wrote here, I should call this array, I should call this interrupt descriptor table. Okay, so we're going to say, when we call this function, we'll say interrupt descriptor table, and we're going to index into that by gate num. And we're going to set the offset field first. So first we'll set the least significant bits. So we'll take the handler address, we'll cast it as an unsigned int, and we will mask off the most significant 16 bits. So if you remember in class, we talked about this bit mask operation, right? A bit mask is a number or an integer that has 1s in the bit positions that we want to keep and 0s in the bit positions that we want to force to 0, right? So this handler address, basically, this is a 32, but you can think about it as a 32-bit pointer or a 32-bit integer, and we want to isolate the least significant 16 bits of it, right? And so the way we're going to do that is we're going to bitwise AND it with this mask here that has 1s in the least significant 16 bits and 0s in the most significant 16 bits. Right, and that's gonna satisfy, basically nuking the most significant 16 bits, right? Okay, so then let's do the same thing for offset 2, but in offset 2, we need to get the most significant 16 bits. So we'll take our handler address, we'll shift it right by 16 bits, and then we'll apply the same mask, right? So what this is going to do is this is going to take the handler address, this is the 32-bit pointer, shift it to the right by 16 bits, and that'll take the upper 16 bits and it will shift them down into the lower 16-bit positions. And then we'll apply the same bit mask to force the top 16 bits to 0. Okay, so those are kind of the 2 most important things. We do need to set these other fields though. We'll set the code segment selector to 1, 0. We'll set the 0 field to 0. And then we'll set the flags field or the attributes field to 8E. All right, cool. So this function will work. So now we just need to call this function once for every gate in our interrupt descriptor table, and we'll just do that from our main function. When we call this function, though, we need to have a handler that we're gonna set up, right? So we actually need to define a function that can be called in the event of an interrupt, right? So when we do that, let's just define kind of a dummy function for that purpose, right? So I'll just make a function up here, and we'll call it we'll say dummy handler, and then it's not going to do anything. So this is normally fine. The one thing about interrupts, though, is that the one difference between interrupt handlers and regular functions is that an interrupt handler uses a special return instruction, right? So a regular function, like our main function or the set IDT gate, it uses a standard return instruction. But at the end of our dummy handler, when we get done, we can't use the same regular return instruction to return from an exception or to return from an interrupt. So we need to tell the compiler that this function is a special interrupt exception handler, and we want to tell the compiler to make sure and use that special return instruction when it compiles the code down into assembly. All right, so the way we do that, GCC has a special kind of a special C addition like this, and this basically tells GCC that it should use the interrupt return instruction at the end instead of the regular function return. We can just basically install this dummy handler in every one of those interrupt descriptor table gates. Okay, so we'll call this function set IDT gate. We'll give it the address of the handler we want to use. This is the address of our dummy handler. And then we'll also just give it k. That's the iterator of this loop, and we'll just have our function install this dummy handler gate in all of the 256 descriptor table entries. Okay, perfect. So we got that. So we got the interrupt descriptor table set up. And so really the only thing we need to do after this is to, well, actually, one other thing, we need to tell the processor where this interrupt descriptor table lives in memory. Okay, so basically the processor doesn't know if we don't tell it, right? So we have to set a special register within the processor that defines the base address of the interrupt descriptor table, and we do that with a special assembly instruction called LIDT, load interrupt descriptor table. All right, and that assembly instruction basically takes the address of an IDT descriptor struct. Okay, so we need to create another struct. This is a special 386 weirdness thing. And basically this is, we'll call it the IDT descriptor. Okay, and the IDT descriptor is a struct that just has two fields in it. It has the limits field, which is the size of the interrupt descriptor table, right? It's just 256 elements long times 8 bytes per element. And then it has a 4 bytes base address of the interrupt descriptor table. Okay, so this struct, we're going to use this struct to define the location of the interrupt descriptor table. Okay, so inside of our main function, we will populate this thing. Okay, so we'll create a new variable IDT desc, and the type of that variable is this struct IDT descriptor. We'll initialize the limit field to be the size of the table, and we will initialize the offset field to be the location of the table. So this is treated, this IDT here, this is the name of our variable which holds the interrupt descriptor table, right? This is a big long array that we created. Where do we create this thing? We created it, oops, I'm sorry, this is called interrupt descriptor table. So let's rename this thing here. Okay. Oops. Yeah. All right. So we called this thing interrupt descriptor table. This variable is an array, right? And so if we just refer in C, if you just refer to the name of an array, that C will replace that with the address of the first element of that array. Okay, and that's what we want, right? We want to tell the processor what's the base address of this array, which holds the interrupt descriptor table. We need to use this LIDT function in order to actually initialize the descriptor table in the 386. Okay, so we'll create a new function here. We'll call it IDT flush, and it's going to take the input of this thing is going to be one of these IDT a pointer to an IDT descriptor element. Okay, and then we're going to just use some inline assembly in order to issue this LIDT instruction. Okay, this is also getting a little bit weird. This is some GCC magic. And so basically GCC allows us to issue some inline assembly instructions, right? So in this case, C does not support, the C language standard does not support using this LIDT instruction. So we have a couple of choices here. If we want to use it, we could write this IDT flush function just in pure assembly. We could create a new assembly file and write a whole assembly language function that does this, just in assembly language, load the IDT, use the LIDT instruction, then returns. But it's kind of a pain in the butt, and it's like, it takes a long time. You're gonna add a new assembly file, so it's making your project kind of a mess. But you could do it that way. The other way to do it is to kind of surgically use one assembly, surgically insert, I should say, one assembly instruction kind of into your existing C file, right? And that's what we're doing here. That's what inline assembly allows us to do, right? So we have a large C file, and then we have this one instruction that we want to stick into this function here. So the kind of the cool thing, I don't know if you consider this cool or not, but the cool thing about GCC's inline assembly is it allows us to use C variables as part of our assembly language instructions, right? So what we want to do when we use this LIDT instruction, we want to give it the argument that we want to give it is the address of this descriptor table. The descriptor table basically tells the processor where to find the interrupt, the interrupt gates or the interrupt descriptor table, right? So basically, we want to include this. We want to use this C variable here in order to pass it as an argument, basically, to this LIDT instruction, right? And GCC inline assembly allows us to do that. So it gives us like kind of these three colons here, right? And, the first colon tells us what are the outputs of this block of inline assembly, right? So this is an output from the assembly back into the C file, right? The second block tells us what are the inputs to the inline assembly, right? These are inputs that are needed by the assembly. These are usually just a list of C variables that are going to be used by the inline assembly block. And then the last thing is called the clobbers, and the clobbers are basically registers that the inline assembly block changes. So if your inline assembly block uses the EAX register without saving it, that would be considered a clobber, right? And so basically it'll overwrite the contents of EAX. So in this case, we don't have anything that we're going to clobber here, right? We're just going to have an input, right? The only thing we're going to be doing here is we're going to be putting inputs from the C program into this inline assembly, and the way we're going to do that is we are going to basically just give it the name of the C variable that we want it to use, and we're going to say treat this as a memory variable, right? So I don't want to really explain all this. I don't really understand it that well, frankly, and it's very complicated. So if you're interested in learning more about the syntax of this inline assembly, if you just search GCC inline assembly on Google, there's a big long document that GNU publishes on this, and they'll tell you way more than you want to know. But just kind of suffice it to say here, this is the syntax that we need in order to get the compiler to produce this LIDT instruction. right? So from down here in our code, after we set up this IDT descriptor, then all we need to do is just call our function IDT flush, and we are going to pass the address of the IDT desk variable. Okay, and this is going to cause the processor to load the address of our interrupt descriptor table. Okay, so now we have an interrupt descriptor table. Okay, and we have initialized all of the gates in the interrupt descriptor table using this for loop here. And then after we initialize them, we have loaded the processor with the address, the base address of the interrupt descriptor table. Okay. So the last thing we need to do is just initialize the PIC, right? The programmable interrupt controller. So the programmable interrupt controller is basically accessible through those I/O ports, right? That x86 processor has like these weird I/O ports that you have to use to work with the legacy devices. And the PIC is basically accessible through that, right? And so basically there's kind of a couple of different initialization commands that we need to pass to this thing, and the process of initializing this thing is called remapping the PIC. Okay, and let me explain what that means a little bit. When I talked earlier about the way the PIC is connected to the CPU, we could just bring up that diagram again real quick. Basically, the PIC is connected to the CPU. I said earlier that it was connected only through, there's only 7 interrupt inputs to this 8259 PIC, right? And I went through the whole process of how, what happens when a peripheral device raises one of those interrupts, how the 8259 communicates with the 386. Well, this is fine. The problem is that on the PC we have more than 7 interrupt sources, right? So you can imagine, like on an early PC, you have you got a bunch of disk controllers, maybe you have a couple of hard disks, you might have a couple of floppy disks, you got I don't know, like a serial port, a mouse, all this different stuff. It ends up being more than 7 interrupt sources. And so just one of these PICs is not going to work. So it's possible to put these 8259s into kind of like a daisy chain mode. And basically the way this works is that the interrupt output of one of the 8259 devices becomes one of the I inputs of the second one. Right, so this is called the master-slave configuration. This is back in the good old days before they were as enlightened as us now, and so they did not have. They called them master-slave. So anyway, that's just what it is, right? And so. So anyway, we have to, when we set this thing up in software, we have to make sure to when we program these devices, we need to do 2 things. First thing, we need to program both PICs, right? There's 2 programmable interrupt controllers on the PC's board, and we need to program both of them. And then we also need to tell them, when we're programming them, we need to tell them that they're in this daisy-chained, or whatever you call it, master-slave configuration. Okay, so the base address of this thing is the base address of the primary PIC, the one that's connected directly to the 386, is IO port 20. So we will use an out instruction to transmit to IO port 20. And we're going to send, the command we're going to send is this reset command, which is hex 11. Okay, and then we'll do the same thing to the secondary PIC that lives at address A0. Okay, so that's the command port for the primary PIC and the secondary PIC. Okay. Okay, so this out, so I guess this should be called out B. So I think, so let's go over to OS Dev and just steal the out B. Okay, so out B is going to allow us to send a command over to the 2 PICs to reset them. That's the first thing we need to do. After we reset them, we are going to set their interrupt offset. This is called remapping the PIC. Okay, why do we need to remap the PIC? Well, when I said before was when we first started with our with this diagram, I said that basically the interrupt gates, right, the first 32 interrupt gates are reserved for CPU exceptions, and then all the gates above that, right, are for hardware interrupts. Okay, and so when the PIC tells the 386 what interrupt is causing the interrupt, right, what device number is causing the interrupt, we don't want it to send the number 0. Let's say if it's interrupt source 0, we don't want it to send the number 0 to the 386 because the number 0 is reserved for the CPU exceptions, right? We wanted to add the 32 offset onto that, right? So if it gets an interrupt from source number 1, then the PIC will add 32 to that. Okay, 1 plus 32 is 33, and then the PIC will present interrupt source number 33 to the 386, right? And when that happens, then it'll actually, the 386 will read interrupt gate number 33 out of its vector table, or out of its whatever they call that, descriptor table. Okay, so we need to remap the PIC. Basically, we just need to tell the PIC that it needs to add an offset to the interrupt numbers every time it gets an interrupt, right? So we're going to send to port number 21. This is the primary PIC. We're going to add the offset of 32, okay, or that would be hex 20. And then to the secondary PIC, we'll send it to port A1, right? This is the data register for these PICs, 21 and A1. We will send offset number 40. Okay, so the primary PIC is gonna, is basically gonna add 32 to all of its interrupt sources, and then the secondary PIC will add 32 plus 8, right? Because the primary PIC takes up 8 interrupts. Okay, good. All right, so we're gonna remap the PIC. All right, and then we are going to tell the PIC that it needs to cascade its interrupts. So we will send this command to number 21. We will send the command 4, which tells the primary PIC that it's going to cascade its interrupts. All right, and then we will send command 2 to the second PIC. Put it in what's called slave mode, right, so that it knows that it's a secondary PIC. Okay, good. All right, and then the second to last thing we need to do is put them both in 8086 mode. I guess these PICs could be configured in 8080 mode or 8086 mode. I don't really know what the difference is between that, and then finally we are going to unmask our interrupts. The PICs actually have like a mechanism inside of them that allows them to selectively disable some of the interrupt sources. So you might say to yourself, hey, I don't want to get any interrupts from the mouse right now, right? I'm busy processing some hard disk transaction, and I don't want to get any interrupts from the mouse. So I want to just selectively disable the mouse interrupts while I am doing this other more important hard disk action. But I want to keep the hard disk interrupts active, right? And so by setting the mask bits on these PICs, you can individually enable or disable each of the 16 different interrupt sources, right? And so basically by setting the interrupt mask to a 1, that's going to disable it, and by setting the mask to a 0, that's going to enable it, right? So let's do this. Let's mask all the interrupts off except for the keyboard interrupt. So we will make this F, that's all 1s. That's going to cause us to basically mask or disable all of the interrupts, FF. Okay, and then we will enable only the keyboard interrupt, which is interrupt source number 1, I think, on the primary PIC. Okay, so one of these is set to a 0, and all of the rest of them are set to a 1, which means they're all disabled except for the keyboard interrupt source. Okay, so now we've written this pick init function, so let's just call pick init from our main. right. And then last thing we need to do is do a global interrupt enable, right? So the processor has a interrupt enable disable feature in it that can just completely enable all of the interrupts or completely disable all the interrupts, right? And then this is controlled by a bit in the flags register, and you can set or clear that bit using an STI or a CLI instruction, right? And if you use an STI, that sets the bit in the flags register, and then all the interrupts get enabled all at once. Or you can clear the interrupt enable bit, and that just disables all of your interrupts. Okay, so yeah, so we're gonna use the STI. So this is a different. These are two different things, right? The unmasking and the pick is independent of the unmasking in the 386 CPU, right? So this is a CPU enable, global interrupt enable. Okay. And then up here on line 69 and 70, this is the pick interrupt enable and disable, right? And so you can enable some of the interrupts in the pick, but then you do a global disable of interrupts in the CPU, right? If you don't want to get any interrupts at all, you can globally disable the interrupts using the CLI instruction, and then you don't have to touch the pick, right? Okay. Anyway, so there we go. So we have all this stuff configured. This stuff down here is also doing keyboard things. So we're just reading from the keyboard status register and reading the scan code. But I don't think we need to do that right now. I'll just turn this into an infinite while loop that does nothing. And so the goal here is that what I'm planning for this function to do is we're going to set up all these gates. We're going to set up the descriptor table, and then we're going to use the LIDT instruction to load the descriptor table address into 386. Then we're going to initialize the pick, and when we turn interrupts on, basically then the keyboard interrupt should be enabled, and if we press a key on the keyboard, it should jump over to our dummy handler, and the dummy handler should run. That's what I'm thinking this should happen, and we'll see if it actually works or not. Okay, so let's open up a new terminal here. I got a lot of terminal tabs, but let's just open up a new one. We'll see if I made any mistakes here. It looks like I did. On line 84. And then line 85 has no member offset. Oh, it's called base, not offset. Okay. All right, looks like it's working. So we're going to go into debug mode here. We're going to do make debug. Now, if you run on Gentoo, this isn't going to work. On Ubuntu, make debug, this was kind of configured for Ubuntu. And the cross debugger on Ubuntu is called gdb-multiarch. On Gentoo, it's the name of your compiler. My compiler is i386 unknown elf, and then instead of GCC, we'll add GDB. This is the name of the GDB for my tool chain. Okay. Yours might be something different. Yours might be i686 or something like that. But whatever your compiler is called, just remove the GCC version from the end of that and add GDB to the end. That's the name of your debugger, right? You can't use the regular old debugger for debugging, for like cross debugging purposes, right? So unless you have a x86 platform, maybe you can, but not on ARM. So let's go in here to this launch QEMU script, and we will replace the name of the debugger with the correct name, and then we'll do make debug again. And this is going to take us into the GDB. It's going to start by booting grub, and then it's going to set a breakpoint at main. Okay, so now we're in GDB. You can use the N command to go to the next line of code. You can use the S command to if you need to step into a function. If you use N, that'll step kind of over the function. If you want to step into a function and then individually step through the lines of code inside that function, use S, right? And then if you just push Enter, it'll do the last thing that you commanded, right? You don't have to keep typing N over and over again. You just push Enter and it'll just keep doing it again. But I don't want to do any of that. I actually want to set a breakpoint up here at my dummy handler. So I'll say be dummy handler. And this is going to set a breakpoint up there. And then I'm going to just push C to continue. And then I'm going to go back over into my QEMU window and I'm going to push a key. Oh no, it rebooted. I think I got some kind of a bug. Okay, so the problem I had here, I just debugged this a little bit. The problem I had here was that the interrupt descriptor, the IDT descriptor entry here, this is the struct that tells the processor what is the address of the descriptor. This struct was not getting put in memory correctly. Basically, I told it when I created this struct, I told it to give me one uint16 limit and one uint32 base. All right, and this basically what it did instead, though. So this should be a 6-byte data structure, right? 2 bytes for the limit, which is just the size of the descriptor table. So 256 times 8 is what you go in there, right? And then 4 bytes for the base. So the total is 6 bytes, right? And I did not have this initially when I wrote this. I did not have this attribute packed. And so for some reason, I don't know why GCC does this, but for some reason it promoted this 2-byte data type here to a 4-byte data type, right? So it was giving me 4 bytes for the limit and 4 bytes for the base. And when the processor got that, it was misinterpreting the address of the vector table. Okay. So anyway, so if you put this attribute packed directive at the end, this is a non-standard C directive that's supported by GCC only. If you put that at the end of this struct, then it will it'll kind of force these things to be packed together, right? So it won't promote this 2-byte data type to a 4-byte size. Okay. So all right. So anyway, what we'll do. So then we'll just go and check if this works. So basically, again, the idea would be that we should be able to go into debug mode. We will set a breakpoint at the dummy handler. Okay, and then we're just going to continue, and so it's just going to get stuck in that infinite while loop, right? So it's going to be spinning in that infinite while loop until I press a key, and as soon as I press a key on the keyboard, it's going to stop what it's doing in the infinite while loop. It's going to save its context, also save the program counter on the stack, and then it's going to jump, it's going to look up in my interrupt descriptor table what is the function that I should call in response to a keyboard event, right? And it's going to find this dummy handler in there because I initialized all of the interrupt gates to be this dummy handler, right? So then it's going to call this dummy handler function. So here I am in dummy handler. Dummy handler doesn't really do anything, right? It just kind of sits there. Probably what you should do in dummy handler is read the scan code from the keyboard controller, but we're not doing that here. And anyway, so dummy handler is just going to continue. So at least the interrupt system works. The one last thing we need to do in order to make this, if this is going to be a keyboard interrupt, let's do this. Let's split this thing off. So we'll have dummy handler be the handler for all of our interrupts except for the keyboard. All right, we'll make one special handler that is for the keyboard only, and I'm going to rename it keyboard handler. Okay. And then, the thing one thing I forgot to do, or I didn't do while I was writing dummy handler, is I need to acknowledge the interrupt at the PIC. All right, and so we're going to write to the control register, the PIC's control register. This is the primary PIC, the one that's connected directly to the 386. We're going to write to that control register, and the value we're going to write is this hex 20, which is just going to acknowledge the interrupt. right? If we don't do this, then the pick is not going to interrupt us again, right? We'll only get the first keyboard interrupt. If we don't acknowledge the first interrupt, it's not going to keep trying to interrupt us, right? So if I push the key again a second time, I'm not going to get a second interrupt because the interrupt controller will think, well, he never acknowledged the first one. I'm not going to keep giving this guy interrupts if he hasn't even acknowledged the first one. Okay, so we're going to act the interrupt. Probably in here we should also, I'll just put a comment in here, probably we want to read the scan code, right? You guys all know how to do that. We talked about how to do that. And then we might want to also print the scan code. We want to do something with that scan code. We want to look up the ASCII code for it. Maybe we want to put the scan code or the ASCII code into a into a queue or something like that, so that we can so that we can read the stuff that the user's been typing. There's a lot of different things you could do here, but I'll kind of leave that to your discretion, whatever you want to do. Right? You could print it to the screen. I don't know, whatever, right? Okay, that's great. So let's do that. And then, all right, cool. So let's just we'll recompile, rerun. Okay. And then we'll set the breakpoint of the keyboard handler. And then we will press a key. Oh no. Oh, I forgot this isn't going to work because I never actually set up the keyboard handler here, right? So I need to go back into my main function here, and I need to overwrite the dummy. It's calling the dummy handler when I press a key. I want to change it so that when I press key number 33, I think it's interrupt 33 for the keyboard handler, that it actually calls the keyboard handler, right? Okay. Let's try that again. Okay, so let's go over here. We'll press a key. We acknowledge the interrupt and we keep going. And then if we press a key again, oh no, maybe we need to actually read the scan code in order for the keyboard handler to. Yeah, maybe I'll just do that. I guess I wasn't going to do your whole homework assignment for you, but I guess maybe I have to. All right, there we go. We get the scan code. That's not an ASCII character, it's just a scan code, so let's see what happens if we push. Yeah, okay, so if we push the key again, then we'll go back to the keyboard handle. So you have to read the scan code, and you have to acknowledge the interrupt if you want this to work. Okay. So the one other thing here I wanted to show you guys, which is kind of cool, is that once you set up the pick, you also get access to this thing called the programmable interval timer, the PIT. The PIT is kind of cool. I mean, it's just basically a counter that interrupts the CPU at a regular interval. And by default, the BIOS sets it up to interrupt, I think it sets it up to interrupt at around 18 hertz. And so what we can do here is we can have another interrupt source here. Let's call this the PIT handler. All right, and the PIT handler is just going to get these PIT interrupts, right? These are regular interrupts that happen 18 times a second. And so, so this is really useful for an operating system if you want to be able to keep track of time. It's really useful to be able to keep track of time. Oftentimes our operating systems only want to, allow one process to run for a short period of time, and then it wants to, we don't want to allow the one process to completely dominate the CPU and not let anybody else use it. So we'll use one of these, we use like a timer interrupt, like the PIT, to periodically interrupt the CPU, which causes us to pass control back to the operating system, and then the operating system can run its scheduler and decide, what should run next. Maybe we want to keep letting the same process run over and over again, or maybe we want to pause the process that's currently running and allow somebody else to use the CPU, right? And that's what the PIT, or the, generally they're called like timer interrupts. That's what a timer interrupt does, right? Just it hands control back to the operating system at a regular interval. And by default, this thing's programmed to interrupt at 18 hertz. But you can change that by writing to some of these output ports. You can initialize the PIT to run at a different frequency. Now, I won't talk about how to do that exactly, but It is possible. If you just look it up on OS Dev, just type in pit OS Dev. There's a bunch of different stuff on there. Okay, but what we could do here is let's do this. Let's say so let's create a static variable here. A static variable is one that is it's like treated as a local variable by the compiler, but it retains its value. It doesn't lose its value when it goes out of scope, right? And this is important because we want to just keep incrementing this variable every time we run the pit handler. We don't want it to get reinitialized every time the pit handler runs again, right? So each time we get a pit interrupt, we will increment the ticks count, and we'll just say if ticks is greater than 18, right? It's an 18 hertz counter, then we will set it back to 0, and then we will increment seconds. Let's make another one of these called seconds. Okay, so we're going to get 18 pit interrupts per second. We'll increment seconds, and then let's display seconds on the screen. Okay, so we'll say we'll make sure seconds is only a single digit number ever, right? So we'll take the seconds mod 10 so that it never gets bigger than 10, and then we'll just say so we're going to take the number of seconds, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And then we're going to add ASCII code 0 to that. That's the ASCII offset, right? So if seconds is 0, that'll be 0 plus ASCII code 0 will actually give us the ASCII code for 0. And then we're going to write that into video RAM. If seconds is 1, that's going to be the integer 1. Add that to ASCII code 0. That'll give us the ASCII code for 1, and then we'll write that into VRAM 0, whatever, right? So this will just display one digit tick count on the screen that's just going to kind of wrap around every time we every 10 seconds, right? Oh, you know what? We forgot to enable it, right? So the pit handler, we need to enable the pit handler by using this. We're going to set the interrupt gate here to the pit handler, and that's going to be interrupt number 32. You can look that up on OS Dev, what the interrupt vectors are. And then the other thing we need to do is we need to also enable interrupt 32. We need to unmask it in the pit, right? So we need to set this thing here. We need to set this interrupt mask so that bits 0 and 1 are equal to 0. And that's going to cause those two bits to be, or those two interrupt sources to be unmasked by the pit. All right, let's try that again. There we go. Okay, so now it's counting up once per second. It's a little slower than once per second. I'm not sure why that is exactly, but it's just counting up once per second. And what's happening is every second you're getting 18 of these pit interrupts, and the pit interrupt is just every time it's just keeping track of this tick counter, right? And that's incrementing that tick counter, and once that tick counter reaches 18, it's incrementing the seconds counter and displaying that on the screen, right? So I think you guys should be able to work with that if you're interested in making your pit work. Maybe we'll do a homework assignment that requires you to get the pit working at some point. It's really not that hard. You just need to create a handler routine for it and then unmask it in the pick. But yeah, anyway, kind of cool. Okay, thanks for watching, and see you next time in class.